A hollow spherical shell of external radius A and internal radius B floats in water. The relative density of the material of the shell is S. So that means that the density of the shell is 1000 times S. Now we are assuming that the density of the inside of this thing is 0. Okay. So the inside is made out of air, or maybe there's nothing there, maybe it's a vacuum, but the density of air can be ignored. Find the maximum buoyancy force that the shell could experience while floating in water. Well, the buoyancy force on a floating object, as we know, acts vertically up. It's got no horizontal component. We know from Archimedes Principle that the magnitude of the buoyancy force is the weight of the liquid displaced. The liquid is water in this case. But the weight of the water displaced depends on the volume of water displaced. So the buoyancy force will go up as we push this sphere below the surface. So if we imagine moving this sphere so it's now below the surface, the buoyancy force is equal to a greater weight of water displaced, because the volume of water displaced now is equal to the entire volume of the object. Okay, so when the object is completely immersed, the buoyancy force is at its maximum. Now, it doesn't matter if it's completely immersed and floating, or it could be very heavy and sinking to the bottom. It makes no difference. The maximum buoyancy force won't change. It only depends on the volume and hence the weight of water displaced. So it doesn't matter how dense it actually is, whether it's floating or sinking. So this quantity will be a constant. Well, we know that it's just the force on the object due to the surrounding liquid. And we know that that force varies linearly with depth. So as we get up here, force vectors are much smaller. Okay, the force is at its greatest here. So the sphere is fully immersed, so the volume of water displaced equals the volume of the complete sphere, a sphere of radius A. So that volume is 4/3 pi A cubed. So that's the volume of the immersed sphere when it's fully immersed, which is equal to the volume of the water displaced. So we multiply that by the density of the water displaced, which is 1000. That gives us the mass of the water displaced. Multiply that by g to give us the weight of water displaced. Prove that if the shell is not totally immersed in the water, then the relative density of the shell S is less than A cubed over A cubed minus B cubed. Okay, so here's the situation. The sphere is not totally immersed. It's floating here, it's in equilibrium, so the buoyancy of it is equal to the weight. Okay, so that's just a condition for equilibrium. The acceleration of the sphere is 0. Okay, let's get the mass of the sphere in terms of the density, rho, and in terms of the volume. Well, all the mass is concentrated in the shell. The inner part is made out of air, or it's just a vacuum, so we ignore its mass. So to get the mass of the shell, we need the density of the shell, which is 1000 times its relative density S, times the volume of the shell. Well, that's just the volume of the outer sphere, 4/3 pi A cubed, minus the volume of the inner sphere, which is also, it's a sphere, so it's 4/3 pi B cubed. So we can factorize out the 4/3 pi. So we 4/3 pi A cubed minus 4/3 pi B cubed. So density times volume gives us the mass, M, of the shell, which is the mass of the entire sphere. Now, we know that the maximum buoyancy is given by this thing here. So the maximum buoyancy would occur, of course, if the sphere was completely immersed. Now this sphere is floating. It's partially immersed. So this relation must hold. If the sphere is just floating and completely immersed, then the buoyancy will equal this. Well, the weight will equal this actually. So if the sphere is just below the surface but not sinking, then its buoyancy is at a maximum because it's displaced the maximum amount of water. So the buoyancy is given by this, and this will also be its weight. So this will be the weight if it's floating but completely immersed, but it must be floating, it can't be sinking. because if it's sinking, then B is not equal to W. You see, we must have the B equal to W. Okay, we can do a load of cancelling for this inequality. We're just cancelling positive quantities, so we don't have to worry about the direction of the inequality. Finally, we divide both sides by a cubed minus b cubed. Now this quantity is positive. We don't have to worry about it being negative and affecting the direction of this. Why is it positive? Well, you can see that a is obviously greater than b. So we get our result. So as long as the relative density of the shell is less than a cubed over a cubed minus b cubed, then the sphere will be partially immersed, which means that it will float. So partially immersed means that part of it could be above the top, some part of it must be above the top, and in the extreme situation it's just floating below the surface of the liquid. But B is always equal to W. As an aside, notice what happens if we let B go to 0. Okay, so the shell fills up the entire sphere. So we have a sphere of radius A. Then S is going to be less than a cubed over a cubed. In other words, S is going to be less than 1. So the entire sphere is made out of the shell of relative density that will have to be less than 1 for the sphere to float. And that makes sense because the relative density of water is equal to 1. So we want the relative density of the sphere to be less than 1. In part 3, we are given that if S is 27 over 19, we have to prove that the thickness of the shell must be less than a over 3. Notice, by the way, that this value of S is greater than 1. So if the floating object was not hollow, then, well, it wouldn't float actually, because the relative density is greater than 1. So if the entire sphere was made out of material relative density greater than 1, it would sink. But you see, we want the overall density of the sphere to be less than 1,000, or the overall relative density to be less than 1. So that depends on the thickness of the shell. Now we can multiply both sides of this inequality by a cubed minus b cubed. This is a positive quantity after all, because a is greater than b, so we won't affect this inequality. Alright, so this is what we get. Okay, we can bring the one, subtract a cubed from both sides. So we have 27 19ths minus 19 19ths a cubed. That's 8 19ths a cubed. And we can multiply everything by 19. That's a positive number. So we get down to this. Now, we're interested in the thickness. So the thickness is the radius of the outer part minus the radius of the inner part. So it's a minus b. Okay, so to get at a minus b, we can rearrange this, take the cubed root of both sides. So as a reminder, we want the thickness to be less than this quantity here. This is given in terms of a. So we need to sub into this quantity, get b in terms of a. So we get a quantity just involving a. So by rearranging this, I just switch this around here. 3b is greater than 2a, and I divided both sides by 3. b must be greater than 2/3 a. So what does that tell us about a minus b? Okay, if b is greater than 2/3 a, if I plug 2/3 a in for b, I'll get a minus 2/3 a, which is 1/3 a over 3. So this is the thickness when b is equal to 2/3 a. This is what we get for the thickness. We get a over 3. But you see that if we take a value of b that's greater than 2/3 a, then we are taking a greater quantity from a. If we take a greater quantity from a, we get a thickness that's going to be smaller than this. So if b is greater than 2/3 a, then the thickness is going to be less than a over 3. In other words, as b goes up, the thickness, which is a minus b, will go down. And that's easy to see from the picture actually. You see, if b goes up, if we increase b, then the thickness a minus b is going to go down. So again, if b is equal to 2/3 a, the thickness is going to equal a over 3. But we know that b has to be greater than 2/3 a. So when b is greater than 2/3 a, when we increase the thickness, when we increase B, the radius of the inner part, the thickness is going to go down. It's going to be less than A over 3. A uniform solid sphere is held completely immersed in 500 centimeters cubed of water by means of a string tied to a point on the base of the container. The tension in the string is 0.0784 newtons. So this force acts away from the point of contact along the string. When 300 centimeters cubed of another liquid of relative density 1.2 is added and thoroughly mixed with the water, the volume of the mixture is 800 centimeters cubed, and the tension in the string is 0.1078 newtons. So notice that the tension of the string increases from 0.0784 to 0.1078 newtons. Now the reason is because the liquid that's added in has greater density than the density of water. The density of water is 1000, or relative density 1. The density of this new liquid is actually 1200. So, in the first part we want to get the relative density of the mixture. Now I want to convert these volumes to meters cubed, so we have to see what 1 centimeters cubed is in meters cubed. To do that we consider a cube of side 1 centimeter. The volume is just 1 times 1 times 1, which is 1 centimeter cubed. But 1 centimeter is 0.01 meters, so 1 centimeter cubed is 0.01 cubed. So we have 0.01 by 0.01 by 0.01. We have 6 decimal places here. You can write this as 10 to the minus 6 meters cubed. Okay, of course the masses are conserved. If we add the mass of the water to the mass of the liquid, we have to get the mass of the mixture. Masses are conserved even if volumes aren't conserved. Actually in this question the volumes are conserved. 500 plus 300 gives us 800. But that's not necessarily the case. Okay, how do we get the mass of the water? We multiply the density of water, which is 1000, by the volume in meters cubed. Okay, so we want to use the correct SI units. So 500 centimeters cubed by 10 to the minus 6. Now, what about the mass of the liquid? Its relative density is 1.2, so its density is 1.2 times 1000. And we multiply that by its volume. So its volume is 300 by 10 to the minus 6 meters cubed. Okay, so what about the mass of the mixture? Well, it's the density of the mixture which we have to find out. We call that rho WL, the density of the water liquid mixture, times the volume. As I said, volume is conserved. Just add 500 and 300. We get, well, we're given that it's 800 by 10 to the minus 6. Okay, for this we get 1075 kilograms per meter cubed. I suppose I better write in the units. So the relative density, which I'll write SWL, is this divided by 1000. It has no units, it's dimensionless. We get 1.075. So this is the density of the mixture relative to water. Okay, let's look at the forces acting on this. Well, we have its weight, which acts vertically down. Its weight is mg, whatever the mass is. And we have a buoyant force acting vertically up, which must be the sum of these two forces for equilibrium. Okay, we're looking at the situation where the liquid is water. Okay, so the tension is 0.0784. We apply Archimedes Principle to get the buoyancy. The buoyancy is the weight of the liquid displaced, where the liquid is water. So the weight of water displaced is the density of water, which is 1000, times the volume of water displaced. So that's the volume of this sphere is V. So the volume of water displaced is equal to the volume of the immersed sphere. So this is the weight of water displaced. So that's Archimedes Principle. Now let's consider the situation where we have the mixture of water and this new liquid. We know that the tension in the string increases to 0.1078 newtons. The weight never changes, it's still mg. But since the tension is increased, for equilibrium, it must be the case that the buoyancy increases. And indeed that makes sense. We know that if the density of the liquid, or the surrounding liquid increases, then the buoyancy increases. Okay, so the upwards forces must equal the downward forces. The magnitude of the upwards buoyancy, WL, that's the water and new liquid mixture, is equal to 0.1078 plus mg. Now we apply Archimedes Principle. So the buoyancy is equal to the weight of liquid displaced. So how do we get the weight of liquid displaced? Well, we want the density of the liquid displaced. That's 1.075. Well, actually, this is 1075. I had the relative density written down. Okay, so the density is 1075. We multiply that by the volume of the liquid displaced. Well, that's equal to the volume of the sphere, which doesn't change, same V as before, of course, times G. So notice that we have two equations in two unknowns. The two unknowns are M and V. Now I think that the easiest way to solve these equations is to take this one here and subtract this one up here. So we have 1075 Vg minus 1000 Vg. Well, that's 75 Vg. If we subtract the right hand sides, if we take this here and subtract this here, the mg's will cancel out. 0.1078 minus 0.0784 is 0.0294. Now, I divided across by 75 just to get Vg. I didn't bother getting V, the volume of the sphere. We don't need that. Now you can take this value for Vg and plug it into one of these two equations. I've plugged it into the top equation. So we have 1000 times Vg. 1000 times this here is 0.392, and that must equal the right hand side, which is 0.0784 plus mg. So we subtract 0.0784 from this number and we divide by 9.81 to get the mass of the sphere. To 3 decimal places you will get 0.032 kilograms. A cylinder contains water to a height of 20 centimeters. A solid body of mass 0.06 kilograms is placed in the cylinder. It floats and the water level rises to 24 centimeters. The body is then completely submerged and tied by a string to the bottom of the cylinder. The water level rises to 25 centimeters. Okay, here is the picture of the object just before it's immersed. The water level is initially 20 centimeters. So we are going to get a handle on the part of the object that's immersed. So that's the part below this line here. Now I'm going to show that same fraction of the object just before it's immersed. Let's call the volume of this part VI, the volume of the part of the object that's immersed. Now one of the questions involves getting the radius of the cylinder. So we're going to consider the volume of the liquid in the cylinder before the object's immersed and relate that to the radius of the cylinder, or the cross-sectional area of the cylinder. So let's get the volume of this liquid. Well, it's water actually. Well, it's the cross-sectional area, which we will call A. Okay, it's in the shape of a circle, so later on we can get the radius of this circle once we found A. Okay, the cross-sectional area multiplied by the height will give us the volume of liquid. So the height in meters is 0.2. So it's 0.2 A. Now let's consider the volume of everything below the surface of the liquid in this situation, after the object has been immersed. Okay, so we want the volume of everything below the surface. Well, that's the portion of the object that's below the surface, VI, plus the volume of the liquid. Well, we have that from here. The height of liquid before immersion, 0.2, times the cross-sectional area A. So the liquid before immersion was in the shape of a cylinder, so we can easily write down its volume in terms of the height and the cross-sectional area A. Later on we will work out the radius, because the area of the cross-section is the area of a circle of radius r. We'll get that later. But notice that we can write the volume of everything below this surface as the height, which in meters is 0.24, times the cross-sectional area A. Okay, so this is in the shape of a cylinder. Height 0.24, cross-sectional area A. So we can actually write the volume of the immersed part of the object in terms of the cross-sectional area of the cylinder. So 0.24A minus 0.2A is 0.04A. In a very similar way, we can work out the volume, the total volume of the object. So let's call the total volume of the object V. We could actually write V as O for object. So let's consider the volume below the surface of the water in this situation. Well, it's equal to the volume of the object, VO, plus the volume of the water. Well, we have that from over here, it's 0.2A. But everything below the surface here is in the shape of a cylinder. So the volume of the cylinder is the height of the cylinder, 0.25 in this case, times the cross-sectional area A. So now we can get the volume of the object in terms of the cross-sectional area A of the cylinder. Now when the water level is 24 centimeters, we know that the object is floating. So by the law of flotation, the weight of the object, W, is equal to the buoyant force on the object, B. It just means that the object is in equilibrium. We know from previous videos that the buoyant force on an object, given by Archimedes Principle, is equal to the weight of liquid displaced by the object. And we know also that the weight of liquid displaced is got by getting the density of the liquid, which is 1000 in this case, it's water, times the volume of the liquid displaced, which is actually equal to the volume of the immersed part of the object, which in terms of the cross-sectional area of the cylinder A is 0.04 A. Okay, so that's density times mass. That's the volume of water displaced, and we multiply by G to get the weight of water displaced. So we set this equal to W for equilibrium, or what's also known as the law of flotation. So what's the weight of the object? Well, it's the density of the object, which I'll call rho 0, times the volume of the object, V0, times G. Well, we know what V0 is in terms of the cross-sectional area of the cylinder. It's 0.05 A. Notice that the A's cancel out, and we can actually work out the density rho 0 of the object. If we divide this quantity by 0.05, we get 1000 times 4/5, which is 800. Now in question 1 we want the relative density of the body. Now the letter S is often used to stand for relative density. Well, that's just the density divided by 1000, which is 0.8. It is no units. In the next question we want the tension in the string, so we have to look at the forces acting on the object when it's tied to the base of the cylinder. Okay, so the string is attached to the base, so it exerts a force on it away from the point of attachment along the string, so it's vertically down. We have the weight. Well, we're given the mass. So the weight has magnitude 0.06 g. Of course, this object is in equilibrium, its acceleration is 0, so the force acting upwards must be equal to the two forces acting downwards. Okay, so the magnitude of upwards forces is the sum of the magnitudes of downward forces. We've got B. Well, actually, we have to be a little careful here. This buoyancy force is different from the buoyancy force here. This buoyancy force is actually involves a greater volume of liquid displaced. So we need to get the weight of liquid displaced. Well, that's the density of the liquid displaced, which is 1000 times the volume of the liquid displaced. Well, that's the volume of the object. The volume of liquid displaced is the same as the volume of the object that's immersed in the liquid. Okay, so I just applied Archimedes' principle. The buoyancy on an object is the weight of the liquid displaced. The buoyancy is not equal to the weight of the object here because the object is not floating. So we can't use the law of flotation. But we can always apply Archimedes' principle. So the weight of liquid displaced is density of liquid times volume of liquid times G. Of course, you can see that we need to find out what A is. Well, we know that the volume of the object is 0.05 A, and we know the density of the object, 800. And we know the mass of the object. I'll write that as M0. We're given the mass of the object in the question. It's here, it's 0.06. So the density of the object, rho O, is the mass of the object divided by the volume of the object. We can rearrange that to get the volume of the object, just interchange rho and V. VO is MO divided by rho O. Okay, so here's the volume. Alright, so the V0 is just this thing here. So we could actually go and get A now if we want to, which is, as a matter of fact, is the last question, the third question. We could answer the third question now and then answer this question. It doesn't matter. So we just equate 0.05 A with this value that we have for the volume. So we need to divide this number here by 0.05. Okay, so we get the cross-sectional area of the cylinder. I'll come back to that in the last part. Anyway, just to go back here, just to finish this. So we've 1,000 times the volume of the object, which is 0.000075. Okay, so working this out, we get the tension. It's 0.015 times G newtons. So in part 3 we want the radius of the cylinder, and you know, this is straightforward. The cross-sectional area is a circle. Area is pi r squared. Working this out, you get 0.0218 meters, or in centimeters 2.18.